makes a function a function?
It's like every x value has like only one y or something like that.
Okay, so x's and y's, I'm hearing that. So if I have x and I have a y, what's something else we call an x? Domain input. I love both of those. Input, domain. We're going to talk a lot about those. What about the y values? What do we call them? The range or the output. Okay? The definition I like for a function says for every input, or each input has exactly one output. That is a function. That Tyler was saying something about the x's having only one y's. That's it. Okay? Each input has one and only one, I think is the verbiage they use. One and only one output. Okay, so if I were to draw a t-chart with x's and y's, x is 2, y is 5, x is 3, y is 7, x is 4, y is 2. Is that a function? Yes. I'm looking at my x's, they're all different. I don't care what my y's are. Okay? If I put a 5 and a 5, is that still a function?
Yeah.
Yes. Does it matter that there's 2 5s in the y, in the output? It does not. Yes, ma'am.
You know what Coach King told us? What? He said that if the X is a girl and the Y is a boy, he said it's okay for a girl to have more than one husband, but not for a guy to have more than one girl. That's funny.
Okay. I have not heard that story.
Oh.
Okay.
I don't remember that, but
I remember. It was 8th grade. You weren't there.
I was there.
Oh, and
He told us in algebra 1.
No, 8th grade. Yay, Coach King. Okay, but if I want to keep my x's and y's going, so as of right now, definitely a function. But if I add 2, 7, is it a function? No. Because if I say 2 is my input, what are you going to say is an output? 5. Some people might say 5, some people might say 7. If there's 2 possibilities, it's not a function. Okay? Not a function.
Is there a name for what that is?
That's not a function. Okay? So, the big piece is, can we test, is it a function? What if I give you a graph? Can I go on? If I give you a graph, is that a function? What do you use to determine if you just see a graph?
Oh, the line.
The vertical line test. You're testing the vertical line test. I only use that if I'm given a graph. What does the vertical line test say?
You should only pass through one point whenever you go straight up.
Somewhere there's a shadow, and whoever's watching this probably can't see my shadow. So I take this and I'm moving it, and I go all the way across. It only passes once. Okay? I'm going to draw another graph. Is the blue line a function?
Yeah.
Yes, function. What about the blue one? You said yes?
Yes.
It's not. Okay, here we go. Yes, function.
Can you draw an example of something?
That's what I'm doing next, but you're not supposed to know that. There are functions that go like this.
No.
Is that a function?
No,
That's a sideways parabola.
Parable.
No, because we pass through up here and down here with the same input. Okay? The green is not a function? And we can check all of that just with a vertical line test. Okay? Not a function. Now, if we want to get into something a little harder, this is something you all have already known. Yes? For the most part, there's a little bit of refreshing going on. Okay? What about an inverse function? If something's a function, does it have an inverse function? What does inverse function mean? Do you remember? Have you heard that before? Okay. Their definition. Recall that for a function f, every element f, oh, we already read this, corresponds to one and only one element y. If a point a, b lines on a line, we don't really care. If a function is defined so that each range element, so every output, is used only once, then it is called a one-to-one function, and it will have an inverse. So now, what did that just say? What makes something a one-to-one function? First, you're checking. Is it a function? Okay. Then, is it a one-to-one function? And I will tell you, if it is, then it will have an inverse.
So what's a one-to-one?
A one-to-one function means that if your outputs, there's only one output for every input. So go in, there's one x and one y. I can't have doubles of the y value of the output. Okay? We're going to test this. Our test. We will do the vertical line test and a horizontal line test. So we're not only going to go up and down to see, we're going to add, is it a horizontal line test to see, is it a one-to-one function? Example, our parabola. If I were to draw some x's and y's, a t-chart. If x is 0, what is y? 0. If x is 1, what is y? If x is 2, what is y? Parabola. What's the formula for parabola?
4.
It's x squared, so it would be a 4. If it's 3, it's going to be 9. But that's all going on the right side.
Yeah.
What about if x is -1?
1.
It's a positive 1. So we're -1, we're still positive at 1. -2, 4. Is y equals x squared a function?
Yes.
Yes. It passes the vertical line test. We've already said that. Okay? Is y equals x squared a one-to-one function?
No, because it's the same.
Because why? There's a couple reasons.
Because
You have outputs that are the same. Or you can check the horizontal line test. My hand does not do a very good shadow.
So you only do horizontal if you're checking for an inverse.
Mm-hmm. Yeah, we're going to pretend that. Try to make it skinny.
So
I'm not good at that.
an inverse function is the same as a one-to-one?
If you have a one-to-one function, then you can have an inverse.
Okay.
But we're going to start graphing some inverse functions. Okay? And I'm pretty sure you've done it now for 2, but we're refreshing because all of this is going to go forward. Okay? So this, not one-to-one. Not a one-to-one function. Meaning it does not have an inverse. If I just leave it y equals x squared. Okay? But could I change something to make it be a one-to-one function? Could I limit the domain? I can, right? What could I do to limit the domain to to make it be a one-to-one function? Could we not have the negatives? Could we restrict? Is it in our power to restrict the domain? Yes, it is. I mean, I look at, there's a square somewhere. We're going to pretend that it's just a square. And I just want to talk about the area of this square. If the side length is 1, what's the area? 1. If the side length is 2, what's the area? 4. The side length is 3, what's the area? 9. Can you have negative side lengths of a square? No. So we could use a real world, some kind of example talking about an actual square. Say, we can't always put in anything we want. So our domain could be restricted. Okay? So if we take away, pretend I'm going to another page. We take away our negatives. So let's say, what do we want to graph? We want to graph y equals x squared. For the domain, I need you to start writing domains as with set notation. We've done this with the little brackets. They're not brackets, they're braces. Right? Where x can be what? First thing we're going to do from algebra 2. I don't think he wrote it like this in algebra 2. But we're going to write it like this going on. Set notation. X can be the set. All the elements of the real numbers. Right? But we want a restriction. Such that x is greater than or equal to 0. Okay? So we can have anything, any x, any real number of x, but where it's greater than or equal to 0. So we can plug in 0. We can plug in 1, 2, 3. Could we plug in a half? Could we plug in 3/4? Yes. Could we plug in pi? Yes. That goes to all real numbers. We can plug in anything we want.
So what does that little thing mean?
This is the elements. X has all the elements of the real numbers.
Basically, just
Okay.
saying that X
X is
is a real number.
all real numbers. Because in algebra, I think that's what he lets you just write that. X is all real numbers. Domain, all real numbers. Okay? This is a way to write it a little easier, but it goes to set notation that we will be doing, continuing with. Okay? And then there's a restriction for greater than or equal to 0. So we're starting, if x is 0, we're a 0. If x is 1, 4, 9. If x is a half, is it a 4? Something like that. Could we do more fractions, decimals? And if we wanted to graph that, we're going to pretend that I'm going to graph here, here, 2, we're at 4, 2, 3, 4. I'm probably not going to make it all the way up to 9. And it's way up here. It's growing exponentially. It's going on to the right, but it is not going anywhere to the left. It's half of a parabola. Is this a function? Yes. Is it a one-to-one function? Yes. So I've taken out all the negatives. I've taken out anywhere it would repeat. Okay? Now, does this graph have an inverse? Yes, it does. Now, in Algebra 2, you probably learned to switch the x and the y. There's a lovely little green box that talks about it. You switch the x and the y in your equation, and you solve y equals again. Okay? Let's look at it, just because. Yeah, I don't like that little green box. Let's read the summary of inverse functions on page 269. The following statements summarize our discussion of inverse functions. In a one-to-one function, each x value corresponds with only one y value, and each y value corresponds with only one x value. We've already said that. Okay, we can't have more x's the same or y's the same. If a function is one-to-one, then f has an inverse of f negative 1. The domain of f the range of its inverse. And we'll talk about that one in a second. And the range of f is the domain. The graphs of f and f inverse f, are reflections of each other along the y equals x. Last but not least, to find the inverse function, follow these steps. Replace f of x with y, or you have y equals, and interchange x and y, solve for y. Okay, so if we have a function, y equals x squared, to solve for the inverse function, we're going to switch the x with the y. So where you see a y, I'm going to put an x. Where you see an x, I'm going to put a y. And then I'm going to solve y equals. How do I solve for y? So what's the square root? Take the square root of both sides. So you have the square root of x equals y. Yes? So how can we graph our x and our y? Is there a restriction automatically for x's that you can plug into the square root of x? Yes, what is it? So you can put in rational, can you put in all real numbers? Yes. But is there a restriction beyond? So I can put in all real numbers. Can you plug in negatives with square roots?
Yes. You can imagine.
So what's the square root of -5?
Oh, sorry. I thought you meant can you square negatives?
No.
Never mind. Then
So-
yes, I agree with that.
So can we plug in negatives? No. We still need x to be greater than or equal to 0. Okay? So if x is 0, what is y? 0. If x is 1, what is y? 1. If x is 2, what is y?
Wait. Oh, sorry.
The square root of 2. Because it's an imaginary number. It is a not real number. Because you don't know what the square root of -5 is, do you? Plug that in your calculator and it's going to tell you error every time.
I thought it equals to negative square root.
No, it doesn't. It does not. You cannot pull that out. So the next one I'm going to see is if I plug in a 4. I'm skipping 3 because it's going to be the square root of 3. It'd be 2. The next one I would know if I put in 9 would be 3. Okay, so if I plot these 0, 0, I plug in 1, 1. So there's 2 points that are exactly the same. What if I plugged in a half? Ooh. Over here I plugged in a half, and I got an output of 1/4. What happens if I plugged in a half? Meaning, question is this graph going to look right like this in between? I had a point down here that was a 1/4, that was a half, and a 1/4. Plug it in your calculator. What's the square root of 1/2? One over the square root of 2, so 1 divided by 1.4 something. 0.7. So 0.7 something something. So at a half, I'm actually going to be pretty close to 1. Okay? And then when I get to 2, it's like 1.4, something like that, like almost 1.5. When I get to 4, where am I? I finally get to 2. When I get to 9, 4, 5, 6, 7, 8, 9, I'm finally at 3. I know this is not a good graph. Yeah, we're going to pretend that's my graph. Can I make some connections for you before we are out of time? Just closely getting there. 2, 4. Input is 2, output is 4. On our inverse function, input is 4, output is 2. Okay? So your x's and your y's will be switched. Input of 3, output of 9. You have an input of 9, output of 3. Okay, the inverse is basically the inverse. Yes. Yes. They also talk about the reflection along the y equals x. It's this line right here. It's going to be about that line. All right. I think that's it.